Hey guys, welcome back to my channel. So today let's talk about the t-statistic and t-distribution. Okay, this is a continuation of the last video. In the last video, we talked about the difference, the relationship, connections between population standard deviation, sample standard deviation, and the standard error of the sample mean. So with that knowledge, you should be in a better position to understand when and why do we use t-distribution and t-statistics. Okay, spoiler alert is when n is small, when the sample is small, and the standard population standard deviation is unknown. So, okay, without further ado, let's get into it. Okay, so let's get started. This is a continuation on the topic of t-distribution or t-statistic. And last time we talked about the difference between population standard deviation and sample standard deviation and the standard error of the sample mean. And with this knowledge in mind, you can understand and what condition can we use t-statistics or t-distribution. So let me first start with the central limit theorem. Okay, central limit theorem, and then or parenthesis when to use z and when to use t. So here z means z distribution or z statistic, and t here means t distribution or t statistic. Okay, so central limit theorem says when sample is large enough, the sample mean follows normal distribution. So I can use this graph. So here we have population. Population is not normal. So i.e. x does not follow normal distribution. So x does not follow normal distribution. And then if you want to use central limit theorem, or if you want to examine the distribution of x bar, you should look at whether the sample is large enough. So statistically, when sample size is at least 30 or more than 30, at least 30 observations, we say this is a large sample. Okay, so this is a large sample. And the central limit theorem says if sample is large and sample mean, right? Sample means follow normal distribution. And if you get all the possible values of sample means, the average of sample mean equals population mean. Okay, and the standard error of sample mean, let me use a different color. Standard error of the sample mean equals population standard deviation divided by square root of n, right? So now it depends whether you have known the population standard deviation. So now let me give you another hierarchy. So if population standard deviation is known, and then the standard error of the sample mean equals population standard deviation divided by square root of sample size. And if the population standard deviation is unknown, and then because you have large sample, you can use S sample standard deviation to approximate, right? To approximate population standard deviation. And then the standard error of the sample mean equals S over square root of n. So that's why last video we talked about the difference between the relationship connections between these three measures, right? Population standard deviation sigma, sample standard deviation S, and the standard error of the sample mean sigma sub x bar. Okay, and if population is not normal and n is small, and then we should use non-parametric test. Okay, so we're not talking about this in today's video, so we use non-parametric test. Okay, so we don't use t-statistic because it doesn't follow t-distribution because population is not normal. And another category, or to use central limit theorem, if you know population follows normal distribution, population is normal or nearly normal, i.e. x follows normal distribution, and then central limit theorem says for any sample size, the sample mean is normal, right? So now let me write this way. for any sample size. So if sample is large enough, and then population is normal, right? You don't need a large sample, but you know that sample is large, and then you can use central limit theorem. X bar follows normal distribution, and average is population mean, and the standard error of the sample mean depends whether you have population standard deviation, right? So now, if population standard deviation is known, because different color, right? Population standard deviation is known, and then standard error of the sample mean just equals sigma over square root of n. And if sigma is unknown, doesn't matter because you have large sample, you can use sample standard deviation to approximate population standard deviation. And then you have standard error of the sample mean equals s over square root of n. Okay? And when n is small, right? The other branch, n is small, it doesn't matter, we can still use central limit theorem. Sample means follow normal distribution because population is normal, right? Population is normal for any sample size. Even if the sample is small, the sample means will follow normal distribution. So let me zoom out a little bit. So the sample mean will follow normal distribution. With the mean, population mean, and the standard error of the sample mean depends whether you know population standard deviation. So now here comes the key part. Let me just use a different color. Which color is good? Let me use this color, a little bit bold. Okay, so like this. So let me use white color first. And then if sigma is known, that's very good. And then the standard error of the sample mean just equals sigma over square root of n. So you know sample means follow normal distribution. You know that the average of sample mean is population mean mu. And the standard error, if you know population standard deviation sigma, standard error is just sigma over square root of n. You always know your sample size. So you know this. Okay? If you know population mean, if you know standard error, right, and then you have complete information about sample mean, you will know what the probability that X bar in any range, right? So, and now this part, this branch, this possibility, right, when sigma is unknown. And before we said, when sigma is unknown, it doesn't matter because n is large enough. We can use s to approximate sigma, right? Sigma is unknown, doesn't matter because we can use s to approximate sigma. But that's only true when n is large enough. We talked about that in the previous video, right? And now sigma is unknown, but sample is small. In this case, s is not equal to sigma, or we cannot use s to approximate sigma. Okay, and in this case, we should consider use t statistic. So we should use t distribution or t statistic. So let me zoom in a little bit. So we need population is normal or nearly normal. If n is small, sigma is unknown, and then you should use t distribution. So this x bar follows a nearly normal distribution, and if this is a mean of x bar always equal to population mean, and the standard error of standard error of the x bar. Now you can only use s because s is a sample statistic. You can always, as long as you have sample data, you can always calculate or compute the sample standard deviation. You want to do this, but the thing is, n is small, and this is actually, you can't use s to approximate sigma. That means this is normal distribution, right? Because x is normal. For any sample size, x bar follows normal, right? For any point, for example, any point along this x bar, this is x, for example, this x bar sub 1, another value x bar sub 2, another value x bar sub 3, right? So to find, you can convert that into, before we learn normal distribution, we convert that into a z statistic. Right? For example, if this is 2.5% and this is 2.5%, and we know the corresponding z-score will be negative 1.96, and corresponding z-score for this point is positive 1.96. That means this point, right, this value of x bar is 1.96 standard deviations above the mean, and this point is 1.96 standard deviations below the mean, right? So it's like here, you're using this, right, let me use this color. X bar follows normal distribution, mean and standard error. For this case scenario, S over square root of n. You can convert this normal distribution to z distribution, right? So if this is 2.5% and this is 2.5%, and this will be negative 1.96, positive 1.96. That means this value, right, is 1.96 times standard error, plus mean, right? So this value is mean minus 1.96 times standard error, right? Same thing here. Right, this we can convert the value of x into a z-score. So this point, z-score of this x bar equals 1.96, and this point is negative 1.96. Same thing for here. Right, x bar follow normal distribution, right? Mean, standard error, and then 2.5%. This is a 1.96 standard error is below the mean, 1.96 standard error above the mean. We call this z-score. Right? That means we convert x bar distribution of x bar, this normal distribution, into a z distribution. Same thing here. Same thing here. So x bar follows normal distribution because n is large enough. Right? Even if population is not normal, we have large sample, x bar follows normal distribution. So this mean and standard error this much. So now you can convert any value of x bar into a z-score. Right? If this is 2.5%, and this will be mean minus 1.96 times standard error. Right? S over square root of n. Right, so this is S over square root of n. So that means that z-score for this point is negative 1.96. Okay, but the thing is, if sample is small and sigma is unknown, and this point is not 1.96 standard deviations above the mean. That means this point, if you write this point as mean plus 1.96 times standard deviation with S over square root of n, this is a wrong standard error, because this should be the right standard error of this x bar. But now you don't have sigma, and in this case small sample, you can't use S to approximate sigma either. So that means this is a wrong standard error, and then you get a wrong estimate, right? So that means this value, if this right area, right, if this area is 2.5%, and the corresponding value of x bar is not 1.96 standard deviations above the mean. So you should not convert the value of x bar into a z-score. In this case, you should convert x bar into a t-statistic, or t-value, or t-score. This is the place you should consider using t. Okay, so now you should convert this value that corresponding to 2.5% on the right tail into a t-statistic. So now let me write here. So you have this. X bar follow normal distribution because population is normal for any sample size. This is a small sample. Average is mean, and the standard error of x bar, now you use S over square root of n. But the thing is, for any point along the x-axis, is the value of x bar, and then you should not convert that value into a z-score. You should convert that into t-score. right? And for example, if this is 2.5%, you should get a value here. How many standard deviation above the mean, but that interpreted as a t-value. So we have a value of x bar sub 1, and then the corresponding t-score for x1 bar equals, if you use Excel, okay, that will be norm, that will be t distribution dot nth, and cumulative probability, which is this area, right? So that's 97.5%. And you should give a degrees of freedom. So that number of observations minus 1. So let's suppose n in this case is 12, and then that's degrees of freedom will be 11. And then you get a t statistic. In this case, t should be greater than 1.96 because t distribution is more spread out. Okay, so let me give you a comparison between the t distribution and z distribution. So if this is a z distribution, standard normal distribution with mean 0, standard deviation 1, and t distribution, so we know that standard normal curves is only one curve, it's unique, right? So the z follows normal distribution or z distribution with mean 0, standard deviation 1. So there's only one z curve. Right? But t curve or t distribution, there are infinite number, right? Infinite number of t distribution, there are many. So t is like this. Let me use this color. T distribution is like this. Had the same mean, but different standard deviation. So t distribution is bell-shaped symmetrical, mean 0, standard deviation depends, and standard deviation, how the value of t dispersed around average 0, or how the value of t dispersed around 0 depends on degrees of freedom. So this depends on degrees of freedom. Depends on degrees of freedom. So as degrees of freedom approaches infinity, t approaches z. So when the sample is large enough, t and z distribution overlaps, or t and z give us very similar statistic, very similar value. For example, if n is 1,000, and then t distribution, z distribution like this, right? Mean is 0, standard deviation is 1. N is 1,000, degrees of freedom 999, and then t distribution like this. So when n approaches infinity, t approaches z. So that's why you see t test and z test doesn't make much difference if n is large enough. Okay, so in sum, to use t distribution, the reason that we use t distribution is sample is small and sigma is unknown, like this branch. But you need the population false normal distribution or nearly normal distribution because you want to use central limit theorem. And when n is small, and n is small, sigma is unknown. If sigma is unknown, you want to use s, but now n is small, s is not approximately equal to sigma. Then if you use z score, z statistic, and you will get this will be very off statistic, very off measure of standard error of x bar. So that's why we have to use t statistic. We can convert the value of x bar into a t statistic. Okay, so here I just give you this Excel command to find the corresponding t value given a probability that x bar in a range. So t dot n find inverse, okay, and then the cumulative probability 97.5% and 11 is degrees of freedom because degrees of freedom basically is n minus 1 here. Okay. Another thing important to know is as n approaches infinity, or degrees of freedom approaches infinity, the t approaches z. Okay, so in reality, degrees of freedom is infinity, right? So that's when to use z, when to use t, and hope you find this video helpful. Any other question, please let me know. Hope you enjoyed today's video and found it helpful. That's when we use t-statistics and t-distribution as, t-distribution as distribution of the sample mean. We need population to be normal or nearly normal to use central limit theorem. And X bar follows normal distribution because population standard deviation is unknown and the sample is small, so we have to use t-statistics to make the better or more accurate estimate. Okay, so any other questions, please comment down below, let me know, send me messages. Okay, see you in the next video. Bye.